Every moment, our universe expands. What sparked the birth of this cosmos, and what forces hold it together? Join us as we delve into the mysteries of dark matter and dark energy, two invisible entities that shape our reality yet remain unknown. According to the Big Bang Theory, the universe began as a singular point, extremely hot and incredibly dense, around 14 billion years ago. Imagine a balloon that is fully deflated. At this moment, it represents the entirety of the universe compacted into an incredibly tiny space. Then, in an instant, this tiny point exploded, not in the sense of an explosion we might envision, but more like an expansion where everything suddenly began to stretch and grow outward. As this expansion occurred, the universe cooled down. The first tiny particles began to form, and as temperatures dropped, these particles combined to create simple elements like hydrogen and helium. Over time, these elements clumped together due to gravity, forming clouds that eventually birthed the stars and galaxies we know today. The universe continued to expand and cool, leading to a complex evolution filled with various structures. This theory is supported by several observations, like the cosmic microwave background radiation, which is a faint glow left over from the early universe, and the discovery that galaxies are moving away from us, suggesting that the universe is still expanding. This continuing expansion is similar to how the surface of a balloon stretches as it inflates. Thus, the Big Bang Theory provides a framework for understanding not only how the universe began, but also how it continues to evolve and change over time. The theory of the Big Bang, which describes the origin of our universe, is supported by several key pieces of evidence. First, we can observe that galaxies are moving away from us in all directions, suggesting that the universe is expanding. This observation aligns with what we expect if space itself originated from a singular, incredibly dense point, spreading out over time. Next, we find a faint background radiation permeating the universe, known as cosmic microwave background radiation. This radiation is almost uniform throughout the sky, and is thought to be the leftover heat from the hot, dense state of the early universe, cooling down as the universe expanded. Scientists estimate this radiation dates back to when the universe was just a few 100,000 years old, providing a snapshot of the very early moments after the Big Bang. Additionally, the abundance of light elements like hydrogen and helium in the universe supports the Big Bang Theory. This production of elements took place during the first few minutes after the explosion in a process called nucleosynthesis, where these light elements formed as the universe cooled. Lastly, the large-scale structure of the universe, such as galaxies and clusters, provides further evidence. The distribution and formation of galaxies align with computer simulations based on the Big Bang model, demonstrating how matter clumped together over billions of years since the initial explosion. Together, these observations build a robust framework that supports the idea that our universe began with the Big Bang, allowing us to understand both its origins and its development over time. In the moments right after the Big Bang, the universe was extremely different from what we know today. It was a hot and dense state, almost like a fiery explosion of energy and particles. Picture a small region of space filled with an unimaginable amount of heat. During this time, temperatures soared to levels that are hard to comprehend, where even the simplest forms of matter couldn't hold together. Initially, the universe consisted mainly of fundamental particles such as protons, neutrons, and electrons, along with a sea of energy. These basic building blocks didn't come together to form atoms yet, because the overwhelming energy caused them to move rapidly and collide with each other. This also meant that light couldn't travel freely. It was constantly being absorbed and re-emitted by those energetic particles. As the universe began to expand, it started to cool down. This cooling allowed the particles to lose energy and eventually start to form simple atoms, mainly hydrogen and helium. This transition was crucial for the universe's evolution. For several minutes after the Big Bang, this process continued, forming the first nuclei in a period known as nucleosynthesis. While this was happening, the universe was still chaotic and full of radiation. It was not until about 300,000 years later that conditions became stable enough for light to travel freely. When that happened, the universe became transparent for the first time, allowing photons to move across the cosmos. This marked the beginning of what we now see as the cosmic microwave background radiation, the afterglow of that intense initial explosion, providing a snapshot of the early universe. Scientists estimate the age of the universe using several interconnected methods, each shedding light on this vast question. At the heart of their calculations is the concept of the expansion of the universe. Imagine the universe as a balloon being inflated. As it expands, points on the balloon representing galaxies move farther apart. By observing how fast these galaxies are receding from us, scientists can backtrack this expansion to determine when everything was together, which is referred to as the Big Bang. To measure this expansion, scientists use a special type of light called redshift. When light from distant galaxies travels to us, it shifts toward the red end of the spectrum as those galaxies move away. This shift provides vital information about their speed and, consequently, how long ago they started moving apart. Another key method involves studying the oldest known stars. By looking at their brightness and chemical makeup, astronomers can gauge their age. This data is used to understand how long stars have been forming since the early days of the universe. The oldest stars provide a timeline that helps researchers piece together the universe's history. Additionally, the cosmic microwave background radiation plays a significant role. This faint glow, which fills the universe, is a remnant of the heat from the Big Bang. By analyzing its detailed properties, scientists can glean insights into the conditions of the early universe, further refining their estimates of its age. When all these methods converge, they suggest that the universe is about 13.8 billion years old. Each research perspective contributes to this understanding, creating a comprehensive picture of our cosmic timeline. Through the harmony of these scientific approaches, we draw closer to unraveling the mysteries of the universe's vast beginnings. The Big Bang Theory is the most widely accepted explanation for the origin of the universe, but several alternative theories challenge or expand upon it. One of the most intriguing concepts is the steady-state theory. This idea suggests that the universe has always existed as it is today, with new matter being continuously created to fill the gaps left by galaxies moving away from one another. In this view, the universe is eternally unchanging and infinite in both time and space, which contrasts sharply with the dynamic and evolving picture painted by the Big Bang. Another alternative is a cyclic model, which posits that the universe undergoes endless cycles of expansion and contraction. According to this theory, the universe expands after each Big Bang and eventually slows down, collapsing back in on itself in a big crunch, only to explode again in another bang. This cycle of rebirth creates an eternal loop of universal life where time is not just linear but cyclical. In addition, the multiverse theory suggests that our universe might be just one of many universes existing simultaneously, each with its own origins. In this view, different universes could arise from various processes, including random fluctuations in energy, leading to a diversity of physical laws and structures. Some scientists even propose the idea that our universe began as a small patch within a larger cosmic landscape, giving rise to multiple realities, each with unique characteristics. These alternative theories provide fascinating perspectives on the universe's origins. They invite us to ponder deeper questions about reality itself, challenging our understanding of time, space, and existence. While the Big Bang Theory remains prevalent, exploring these alternatives widens our horizons and emphasizes the complexity of cosmic beginnings. Dark matter is a fascinating and elusive substance that makes up a significant portion of the universe's total mass. Imagine adding invisible bricks to a building. Even though you can't see the bricks, they greatly influence how the structure stands and functions. Similarly, dark matter does not emit light or energy, making it invisible to our current instruments. We cannot see it directly. Instead, we know it's there because of its effects on galaxies and clusters of stars. Scientists first noticed dark matter's influence when they observed that galaxies were spinning much faster than expected. If only visible matter were present, these galaxies would fly apart due to the speed at which they rotate. However, they stay intact, suggesting that there is additional unseen mass, dark matter, providing the necessary gravitational pull to hold them together. The mystery of dark matter lies in its undetectable nature. Despite extensive studies and indirect evidence pointing to its existence, we have yet to identify what dark matter is made of. Many theories suggest it could be composed of unique particles that don't interact with light or normal matter, like anything we encounter in our everyday lives. Some scientists even propose it might consist of exotic forms of matter that defy our understanding of physics. This unknown aspect adds to the enigma of dark matter, driving scientists to explore various possibilities through experiments and astronomical observations. As they delve deeper, the quest to unravel the secrets of dark matter not only promises a greater comprehension of the universe, but also challenges our fundamental concepts of what the cosmos is made of. Dark matter plays a crucial role in shaping the structure and dynamics of galaxies. While it cannot be seen directly, dark matter is believed to make up a significant portion of the universe's total mass. Think of it as an invisible framework that holds galaxies together. When galaxies form, they are drawn together by gravity. Regular matter, which makes up stars, planets, and gas, is not enough to explain the movements we observe in galaxies. For instance, scientists have noticed that stars at the edges of galaxies are moving much faster than would be expected based only on the visible matter present. This discrepancy suggests that there is much more mass present, exerting additional gravitational forces. Dark matter creates a gravitational halo around galaxies. This halo provides a gravitational pull necessary for galaxies to form and hold their shape. It ensures that once these magnificent structures develop, their stars and other contents remain bound within them, preventing them from flying apart. Furthermore, dark matter influences how galaxies interact with one another. When two galaxies approach each other, the dark matter halos can lead to complex gravitational interactions, sometimes resulting in beautiful mergers. These events can trigger the formation of new stars, altering the galaxy's appearances and behaviors. Fundamentally, dark matter acts as an unseen architect, guiding the assembly of galaxies and assuring their stability, ultimately helping to define the vast cosmic landscapes we observe today. Its mysterious presence showcases how much we still have to learn about the universe. Dark matter is one of the biggest mysteries in our universe. While it cannot be seen directly, scientists know it exists because of its effects on galaxies and cosmic structures. The main leading hypotheses about the composition of dark matter revolve around a few key ideas. One prominent hypothesis suggests that dark matter is made up of particles that are different from those that compose ordinary matter, such as atoms. These particles are known as weakly interacting massive particles, often abbreviated to WIMPs. The name comes from their expected size and the fact that they interact very weakly with regular matter, making them nearly invisible to traditional detection methods. If these particles exist, they would cluster around galaxies, contributing to the gravitational forces that hold them together. Another possibility is that dark matter consists of actions, which are hypothetical particles thought to be very light and similarly weakly interacting. Scientists are exploring this idea further. Additionally, gaining knowledge about dark energy may also inspire advancements in technology and methods of exploration. By understanding how this force operates, we might develop innovative ways to observe the universe and gather data on distant galaxies, potentially leading to discoveries we have yet to even imagine. Solving the mystery of dark energy is not merely an academic exercise. It could fundamentally alter our perception of reality, expanding our horizons and deepening our connection to the cosmos. The implications would reach far beyond science, influencing everything from philosophy to our collective future. As we strive to understand our universe more deeply, dark energy is one of the most intriguing puzzles in modern astrophysics. It makes up about 70% of the universe, yet its true nature remains elusive. Currently, we understand dark energy as a force that drives the accelerated expansion of the universe. Imagine the universe as a balloon being blown up. The more air you add, the faster it expands. Dark energy acts like that air, pushing all galaxies apart and causing the universe to stretch ever further. If we successfully solve the mystery of dark energy, it could completely change how we view the cosmos. For instance, understanding dark energy might reveal new laws of physics, reshaping our understanding of forces and how they interact on a cosmic scale. This could lead to groundbreaking insights about the creation of the universe, the formation of galaxies, and even the fate of the cosmos itself. Moreover, unlocking the secrets of dark energy might illuminate the relationship between energy, matter, and the fabric of space-time. This could lead to profound insights into the beginnings of the universe, perhaps even redefining concept of time and space. As a black hole is a region in space where gravity pulls so strongly that nothing can escape from it, not even light. This immense gravitational force arises from the collapse of a massive star. Essentially, when a star exhausts its nuclear fuel, it can no longer support its own weight. If the star is sufficiently massive, it will undergo a supernova explosion, which blows off its outer layers. What remains is a core, which can continue to collapse under its own gravity. As the core contracts, it forces all its mass into an incredibly small space. This process creates an intense gravitational field, resulting in the formation of a black hole. The boundary surrounding this region, the point of no return, where escape becomes impossible, is known as the event horizon. Once something crosses this boundary, it is inexorably drawn into the black hole. Interestingly, black holes come in different sizes. Stellar black holes are formed from individual stars, while supermassive black holes, found at the centers of galaxies, have masses millions or even billions of times greater than the Sun. Their formation is still a topic of research, but they could arise from the merging of smaller black holes or the direct collapse of massive gas clouds in the early universe. Black holes represent one of the universe's most fascinating phenomena, revealing just how extreme the laws of physics can be. The event horizon is a crucial boundary surrounding a black hole. Imagine a dark point in space where the force of gravity is so intense that nothing, not even light, can escape. Once it crosses this boundary, it marks the point of no return. If an object ventures inside the event horizon, it will be pulled inexorably toward the center of the black hole, a region known as a singularity, where gravity is thought to become infinite. This boundary holds significant importance for several reasons. First, it defines the limits of our observable universe regarding a black hole. Anything that crosses the event horizon becomes invisible to outside observers because no information can come back to us. This makes the event horizon a fascinating puzzle for scientists, highlighting the mysteries of gravity and the nature of space and time. Moreover, the event horizon plays a role in understanding how black holes interact with their surroundings. It affects the behavior of matter and energy near a black hole, influencing the formation of accretion disks, rings of gas and dust that swirl around black holes before getting drawn in. Additionally, the study of the event horizon leads to questions about fundamental physics, such as the nature of gravity, the laws of thermodynamics in extreme settings, and even ideas about the potential existence of parallel universes. Scientists use highly sensitive detectors to capture these minute differences, almost like an artist identifying strokes in a painting. Once the data is collected, researchers meticulously analyze it using advanced computer models. They look for patterns that reveal how matter and energy were distributed across the universe so long ago. This process also involves comparing observations with theoretical predictions made by cosmological models, allowing scientists to refine their understanding of fundamental questions such as the rate of the universe's expansion and the nature of dark matter and dark energy. Through this careful study, scientists reconstruct a picture of the universe's infancy, enhancing our understanding of how it evolved into the cosmos we observe today. The cosmic microwave background is not just background noise. It is the oldest light we can see, and its study is crucial for unlocking many mysteries about the universe's origins. Cosmic radiation, particularly the cosmic microwave background radiation, serves as a crucial tool for testing cosmological models. This radiation is like a faint afterglow from the early universe, akin to a snapshot taken when the universe was only a few 100,000 years old. By studying it, scientists can glean important information about the universe's origin, composition, and evolution. Think of this radiation as a relic carrying information about the conditions that existed just after the Big Bang. As it travels through space, it leaves traces of the density fluctuations that occurred in those early moments. These fluctuations are pivotal because they eventually led to the formation of galaxies and larger structures we see today. By analyzing the patterns and temperature differences in this radiation, researchers can validate or challenge theoretical models about how the universe expanded and evolved. Moreover, different cosmological models predict varying amounts and patterns of such radiation. When scientists compare their observations of cosmic microwave background radiation with predictions made by models, they can assess which theories hold up under scrutiny. Differences in expected versus observed data can lead to revisions of existing models, or even prompt entirely new theories. Essentially, this radiation acts as a cosmic messenger, informing us about the very fabric of the universe and helping us refine our understanding of fundamental concepts such as dark matter, dark energy, and the rate of cosmic expansion. It is a central piece of the puzzle in the quest to understand the universe's history and its future. The universe, when viewed on a grand scale, is a vast and complex tapestry of structures devoid of any simple form. At its largest levels, it resembles a web woven from galaxies and clusters of galaxies that form an intricate pattern through vast stretches of emptiness known as voids. Galaxies are not scattered randomly. Instead, they are grouped together in clusters, which can contain hundreds of thousands of them, held together by gravity. Beyond these clusters, There are superclusters that consist of several clusters of galaxies, all interconnected by filaments of dark matter, a mysterious substance that does not emit light but influences the gravitational forces within the universe. This structure plays a crucial role in how galaxies interact and move across the cosmos. As you zoom out even further, you encounter enormous voids, the largest gaps in this cosmic web, that can be billions of light years across, where few galaxies reside. These voids form a significant part of the universe, showcasing the contrast between the dense regions filled with galaxies and the emptiness that separates them. Additionally, the universe is expanding. This means that galaxies are moving away from each other over time. This expansion causes the fabric of space itself to stretch, creating more distance between distant galaxies. As a result, the universe appears to be growing larger, a phenomenon that has intrigued scientists since its discovery in the early 20th century. Overall, the large-scale structure of the universe is a remarkable interplay of density and emptiness, connecting everything with gravitational threads that bind galaxies, clusters, and vast voids into one magnificent cosmic web. Cosmic filaments are vast structures in the universe resembling a web that stretches across the cosmos. Imagine looking at a gigantic spider's web, where the strands are composed of galaxies and dark matter. These filaments represent the largest known scale of cosmic organization, playing a critical role in the formation and distribution of matter in the universe. At the heart of this grand design are the clusters of galaxies that sit at the intersections of these filaments. While the filaments themselves act as the highways through which matter flows, over billions of years, gravity pulls gas and dark matter into these threads, leading to the formation of stars and galaxies along their lengths. This process creates a vast network that can range from filamentary structures that are millions of light years long to smaller ones that are only a fraction of that size. Cosmic filaments are part of a larger framework known as the cosmic web, which outlines how galaxies and clusters are interconnected in 3 dimensions. The structural arrangement includes not only filaments but also voids, vast empty regions that contain very few galaxies. Understanding this web is crucial for astronomers, as it helps explain both the large-scale structure of the universe and the dynamics of galaxy formation and evolution. Cosmic filaments serve as the backbone of the universe, illustrating how galaxies are distributed through intricate, ever-expanding patterns shaped by the forces of gravity and the unseen influence of dark matter. Galaxies are not scattered randomly throughout the universe. They are organized in a complex and fascinating structure. Imagine the universe as a vast web. Within this web, galaxies form clusters, which are groups of hundreds to thousands of galaxies held together by gravity. These clusters can be found in larger collections known as superclusters. Superclusters can stretch over immense distances, often containing multiple clusters and thousands of galaxies packed together. Between these clusters and superclusters, there are vast empty spaces called cosmic voids. These voids can be thought of as the regions of the web where there are very few galaxies. Further, when we zoom out and look at the big picture of the universe, we find that galaxies tend to be arranged in long, thin filaments and walls. This structure results from the early universe's conditions and the gravitational forces acting on matter over billions of years. The gravitational pull of nearby galaxies influences their motion, leading to this organized arrangement. As we study this cosmic layout, we discover that it reflects the universe's history, showing where matter clumped together in the moments after Big Bang. The motion and distribution of galaxies not only enhance our understanding of the universe's evolution, but also provide clues about dark matter and dark energy, 2 mysterious components that shape our universe but remain challenging to understand fully. The universe is filled with vast clusters of galaxies, and these celestial gatherings hold many mysteries about their formation and evolution. At their core, galaxy clusters consist of hundreds to thousands of galaxies bound together by gravity, along with hot gas and dark matter. One of the primary mysteries is how these clusters initially formed. Scientists believe that in the earliest stages of the universe, tiny fluctuations in density created the seed from which clusters grew, but the exact mechanisms of this growth are still not fully understood. Another intriguing aspect is the role of dark matter in cluster formation. Dark matter makes up a significant amount of the universe, yet it does not emit light, making it difficult to study directly. Its presence is inferred through gravitational effects. The relationship between visible matter like stars and galaxies and invisible dark matter in clusters poses many questions. How do these 2 components interact over time? Understanding this relationship could unveil essential details about the universe's structure. Further complicating the picture is the evolution of clusters over billions of years. They change significantly, sometimes merging with other clusters, undergoing processes known as hierarchical growth, where smaller structures combine to form larger ones. The dynamics of these mergers can lead to immense energy releases, observable as shocks in the hot gas surrounding the galaxies. Scientists are eager to understand how frequently these events occur and their impact on the evolution of the galaxies within the clusters. Moreover, the distribution of galaxies within clusters can also be puzzling. Some galaxies appear to be spinning rapidly, while others seem to be moving toward their cluster's center. This diversity raises questions about the history of each galaxy and the environment's influence on their formations. Lastly, ongoing research is investigating the role of cosmic events like supernovae and their explosions in shaping the gas surrounding galaxy clusters. These explosions might change the temperature and density of the gas, which can affect galaxy growth and behavior within the cluster. As scientists continue to explore these questions using telescopes and simulations, they inch closer to unraveling the mysteries of galaxy clusters, providing deeper insights into the universe's formation and evolution. Understanding the structure of the universe is crucial for unlocking answers to many larger cosmological questions. Imagine the universe as a vast web where each strand represents galaxies and clusters of galaxies, interconnected and guiding the flow of cosmic matter and energy. By studying how this web is woven together, scientists can uncover the underlying rules that govern the cosmos. One significant question revolves around the origins of the universe. The way galaxies are distributed gives clues about how the universe began to expand after Big Bang, shedding light on fundamental processes that shaped our existence. By analyzing the patterns in cosmic structures, researchers can trace back in time and explore how the universe evolved over billions of years. This understanding also relates to dark matter and dark energy, two mysterious components that significantly influence the universe's behavior. While dark matter acts like glue, holding galaxies together, dark energy drives the universe's accelerated expansion. By mapping how visible matter interacts with these unseen forces, scientists gain insights into their nature and the overall energy balance of the cosmos. Furthermore, comprehending the universe's structure aids in refining models of cosmic evolution. These models help predict the universe's future, offering a glimpse into its fate. Will it continue expanding indefinitely, or will gravitational forces eventually lead to a collapse? Each answer guides our understanding of the cosmic timeline, illuminating the past, present, and potential futures. In short, the universe's structure is like a cosmic map, guiding scientists on a journey of discovery. By piecing together complexities, they not only answer immediate questions about its formation and evolution, but also address profound inquiries about our place within this vast, ever-changing cosmos. Scientists define time in the context of the universe as a measure of change and progression of events. To grasp this concept, think of time as a continuous river flowing steadily forward, marking the moments that shape the cosmos. This river encompasses everything from the tiniest particles to the vast movements of galaxies. In a broader sense, time is not merely a ticking clock. Instead, it relates to the way objects interact in space. For instance, when we observe a star exploding in a supernova, the event timing offers insights into the life cycle of that star and the energy expelled into the universe. Time helps us understand evolution, whether it's the formation of planets or the orbit of satellites. In the realm of physics, Albert Einstein revolutionized our understanding of time by linking it with space, a concept known as space-time. He suggested that time can stretch or contract depending on the strength of gravity and the speed at which an object moves. Essentially, when traveling close to the speed of light, time behaves differently than it does at rest. This blending of time with the fabric of space demonstrates that time is not a fixed entity. Rather, it's intertwined with the universe's dynamics and can be influenced by various factors. Thus, for scientists, time serves as a critical framework for exploring and explaining the universe's behavior and changes, allowing them to decode the mysteries of existence and the unfolding story of the cosmos. The idea that time might be an illusion or does not follow a simple linear path has intrigued scientists and philosophers for many years. One prominent theory comes from the realm of physics, particularly within the framework of relativity. According to Albert Einstein's theories, time and space are intertwined in what is called space-time. This means that the passage of time can vary depending on speed and gravity. For example, an object moving very fast or in a strong gravitational field experiences time differently than something at rest or in a weak gravitational field. This challenges our everyday understanding of time as a constant experience. Another compelling perspective comes from quantum mechanics, where the behavior of particles at very small scales does not always conform to the straightforward flow of time. In some interpretations, events can appear to happen out of sequence, suggesting that the timeline of reality is much more complex than we perceive. Additionally, the philosophical argument known as eternalism posits that past, present, and future are equally real. In this view, time is not a moving line from the past to the present and into the future, but rather a vast landscape where all points exist simultaneously. This viewpoint radically shifts how we consider events, suggesting that experiences are merely our perceived snapshots of a more tangled framework. All these theories paint a picture of time that is far more intricate than a simple journey from one moment to the next, inviting us to rethink how we understand our world and our existence within it. The idea of time travel captivates our imaginations, yet its roots lie in the serious study of modern physics. At the core of this concept is Einstein's theory of relativity, which describes how time is not a constant, as we often perceive it, but rather bends and stretches based on speed and gravity. For example, astronauts on a high-speed journey through space or at significant altitudes experience time differently than people on Earth. Their clocks tick slightly slower, a phenomenon called time dilation. Moreover, the notion of traveling back in time stays even deeper discussions. Some scientists consider hypothetical scenarios where time loops could exist, much like the idea of a wormhole that connects different points in space and time. If one could enter such a tunnel, it might theoretically allow a person to jump to an earlier moment in their life. However, these ideas raise complex questions. What happens if someone were to change something significant in the past? This is known as a grandfather paradox, leading to intriguing debates about causality and the nature of time itself. In addition to relativity, quantum mechanics introduces another layer of complexity. Some interpretations suggest that multiple realities or timelines could exist simultaneously. This notion might hint at the possibility of altered paths existing in parallel dimensions, allowing for a different kind of time travel without creating contradictions. While time travel remains speculative and challenged by our current scientific understanding, it pushes the boundaries of physics, encouraging deeper exploration of the universe's mysteries. As scientists continue to study the nature of time, space, and their interconnection, the quest for understanding time travel remains an exciting frontier in modern physics. Time is a fundamental aspect of the universe that helps us make sense of how things operate under the laws of physics. It's like a backdrop against which all events unfold. In our everyday lives, we perceive time as a linear progression from the past to the present and into the future. This understanding also guides scientists in exploring everything from the movement of planets to the behavior of tiny particles. In physics, time is often used to measure the intervals between events. For example, when we describe how far something is moving, we relate distance to time. If a car travels a specific distance and we know how long it took, we can calculate its speed. This relationship is crucial because it helps bridge the gap between motion and change. Additionally, time is essential in the theory of relativity, which reshapes our understanding of space-time and gravity. According to this theory, time is not a separate entity but rather intertwined with space to create what we call space-time. In simple terms, the effects of gravity can alter the flow of time near a massive object like a planet or star. Time can slow down compared to a place with less gravitational pull. This means that two observers, one close to a heavy mass and another far away, will experience time differently. Moreover, in the realm of quantum physics, time plays a unique role. Many processes occur at extremely small scales, and the behavior of particles can sometimes seem random and unpredictable. The way these particles interact over time helps scientists understand the underlying rules that govern their behavior. Ultimately, time is not just a measure, it shapes the way we understand and interpret the physical world. From the ticking clock of our daily lives to the vastness of cosmic events, time is woven into the very fabric of reality, guiding the motions and interactions of everything around us. Recent advancements in physics have opened up new avenues of thought regarding time, challenging our classical understanding of it as a simple linear progression from past to future. Traditionally, we see time as a constant, something that ticks away uniformly like a clock. However, new theories suggest that time might not operate in such a straightforward manner. One of the most intriguing concepts has emerged from studies on quantum mechanics. At the smallest scales, particles behave in ways that defy our conventional ideas about cause and effect, suggesting that the sequence of events can exist in a superposition where multiple outcomes happen simultaneously. This introduces the idea that time may not be a fixed path, but rather a more flexible and interconnected experience. Furthermore, the theory of relativity, put forth by Albert Einstein, gives us a different perspective on how time can change depending on speed and gravity. Time can actually run faster or slower depending on how close you are to a massive object or how fast you are moving relative to another observer. This means that time is not just about the ticking of a clock. It is influenced by the fabric of space itself. Researchers are also exploring the possibility of time being intertwined with dimensions of space, leading to the notion of time as part of a larger, more intricate structure. The idea that space and time are interwoven reveals that our straightforward comprehension of time may need a significant update as we delve deeper into the universe's fabric. These advancements are pushing scientists to reconsider fundamental questions. Is time an illusion? Can it be reversed? What happens to time in extreme conditions like near black holes? Each new exploration not only expands our understanding of the universe, but also invites us to rethink our place within it, alongside the very nature of reality itself. Dark flow is a fascinating phenomenon in cosmology that suggests the existence of a mysterious influence on the motion of galaxy clusters. To understand it, imagine the universe structured like a vast expanding ocean, where galaxies float like boats. Most galaxies move with the inflow determined by the expansion of the universe. However, dark flow indicates that some galaxy clusters seem to be moving in a specific direction, as if being pulled by an unseen force beyond the ordinary gravity we understand. This strange behavior was first detected through observations made with specific instruments that measure the cosmic microwave background radiation, which is a faint glow left over from the Big Bang. By analyzing tiny temperature variations in this ancient radiation, scientists noted that certain galaxy clusters appeared to be moving toward a particular area of the sky, located in the direction of the constellations Centaurus and Hydra. This motion seemed to defy the gravitational influences of known structures in the universe and hinted at the possibility of some vast and distant entity affecting their movement. The implications of dark flow lead to many intriguing questions. It suggests that there may be regions of mass we cannot see, perhaps due to the presence of structures beyond our observable universe. Understanding dark flow could unlock new insights into the nature of the cosmos, shedding light on forces and elements we have yet to fully explain. Dark flow is a fascinating concept that suggests some regions of the universe are moving in a specific direction, influenced by forces beyond what we can currently see or understand. The evidence supporting the idea of dark flow primarily comes from observations of galaxy clusters and the cosmic microwave background radiation, often referred to as the afterglow of the Big Bang. Researchers have studied the movement of galaxy clusters, which are large groups of galaxies held together by gravity. By measuring their motions, scientists notice that some of these clusters appear to be moving in a consistent direction, as if being pulled by an unseen force. This is particularly interesting when you consider that many galaxies are distributed fairly evenly across the universe. The fact that some are all moving toward the same area could suggest an influence that aligns more with the scale of the universe itself. In addition, when scientists studied the cosmic microwave background, they found slight variations in temperature across the sky. These variations hint to the early universe's density fluctuations, but some researchers also see patterns that suggest a larger structure may be affecting these measurements. This could indicate that large masses, perhaps outside our observable universe, are exerting influence on everything within it, contributing to the phenomenon of dark flow. While these observations are intriguing, they do not provide a complete picture. Dark flow remains a topic of debate among scientists. Some argue that the observed flow might result from local gravitational effects or other known cosmic structures. Continued research is essential for confirming the existence of dark flow and understanding any implications it may have for our knowledge of the universe. For now, it stands as a captivating mystery in the vast expanse of space, urging scientists to delve deeper into the fabric of cosmic existence. Dark flow is a fascinating phenomenon that reveals more about the universe's expansion and the motion of galaxies. Imagine the universe as a vast ocean where galaxies drift like boats. While these boats generally move according to the expansion of the universe, dark flow suggests that some are being pulled by unseen forces, rather like currents in the water. Observation of galaxy clusters indicates that they appear to move in a specific direction, pointing to a coherent flow that does not align with the standard model of cosmic expansion. This movement hints at the presence of mass that is not directly observable, perhaps related to structures beyond the observable universe. This uncharted territory raises intriguing questions. If dark flow exists, it implies that there are larger cosmic structures influencing our local group of galaxies, creating a sort of cosmic wind. Understanding this flow challenges scientists to rethink how these massive gravitational influences operate on a grand scale. The concept of dark flow also suggests that our universe may be part of a larger multiverse, with other regions of space that are also interacting with us. Dark flow offers a glimpse into the hidden forces acting across greater distances than we can currently see. It motivates researchers to refine their understanding of cosmic movements and the architecture of the universe. As scientists continue to study these phenomena, dark flow may help illuminate the mysteries of gravity and the large-scale structure of galaxies, drastically changing our view of the cosmos. Dark flow refers to a mysterious phenomenon observed in the large-scale motion of galaxy clusters, suggesting they are moving in a particular direction at unexpected speeds. Scientists have developed several hypotheses to explain this phenomenon, each trying to unravel the deeper mysteries of our universe. One major hypothesis is that dark flow arises from gravitational influences beyond our observable universe. Imagine the universe as an ocean of galaxies, but beyond the horizon, there could be vast structures that we cannot see. These unseen regions might exert a pull on the galaxy clusters, causing them to move in a specific direction. This idea aligns with the notion that our universe is not neatly contained, but rather exists within a much larger and possibly more complex cosmic structure. Another possibility suggests the existence of a significant mass concentration, like a supercluster or a series of massive galaxy clusters, that act like a gravitational anchor. This massive collective could be influencing the motion of other galaxy clusters, pulling them along with the flow. Such massive structures could serve as a source of the dark aspect of dark flow, suggesting unseen forces are in play in the cosmos. Some scientists also consider the role of dark energy, a mysterious force believed to be driving the accelerated expansion of the universe. While dark energy typically causes galaxies to move apart, it's conceivable that it could also influence the motion of galaxy clusters in unexpected ways. Understanding the interplay of dark energy and dark flow remains a fascinating area of research. As researchers gather more data and refine their observations, they hope to shed light on this cosmic drift, revealing the underlying mechanics of the universe and perhaps uncovering new realms of physics that lie just beyond our current understanding. Each hypothesis provides a glimpse into the complexities of the cosmos, highlighting the ongoing journey to grasp the profound nature of dark flow and its implications for our understanding of the universe. The dark flow mystery intrigues scientists as it suggests that our universe may not be quite as uniform and isotropic as we once thought. Dark flow refers to the strange, coordinated movement of galaxy clusters that seem to drift in a specific direction, hinting at some unseen force or structure beyond our observable universe. This could mean that there are larger structures, possibly from a past universe or regions beyond what we can currently detect, influencing these movements. If researchers were to resolve the mystery of dark flow definitively, it could lead to a significant shift in our cosmological theories. For instance, it might challenge a widely accepted model that the universe is homogeneous, meaning similar in all directions when viewed on a large scale. Instead, evidence of dark flow could support the idea that there are vast cosmic structures and phenomena influencing galaxies over immense distances. Additionally, new insights into dark flow could lead to re-evaluating the nature of dark energy, the mysterious force thought to be causing the accelerated expansion of the universe. If these galaxy clusters are being pulled by something beyond our observable universe, it raises questions about the dynamic nature of space itself. Such discoveries would not only impact theoretical physics, but might also redefine our understanding of the universe's history and evolution. We could begin to perceive galaxies not as isolated entities, but as part of a much greater cosmic web, interconnected in ways we are just beginning to understand. Ultimately, resolving the dark flow mystery could invite new questions and foster innovative theories, urging us to rethink our place in the vast and complex universe. For life to exist beyond Earth, certain conditions are generally considered essential. These conditions center around the presence of elements, energy sources, and stable environments. The first crucial element is water. Life as we know it relies heavily on water, which acts as a solvent that facilitates chemical reactions necessary for biological processes. Scientists often look for planets or moons where liquid water might exist. Another fundamental requirement is an energy source. Life needs energy to grow, reproduce, and maintain itself. On Earth, the most common energy source is sunlight, which drives photosynthesis in plants. However, other forms of energy could support life, such as the heat produced by geological activity or even chemical energy from minerals. Additionally, the right chemical elements must be present, primarily carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur. These elements combine to form the building blocks of life, such as proteins and nucleic acids, which are vital for cellular function and reproduction. Stable environmental conditions are also critical. This includes a suitable temperature range and atmospheric conditions that can protect life from harmful radiation and provide necessary gases for respiration and photosynthesis. Too much temperature fluctuation can pose risks to any potential living organisms. Finally, a planet or moon need to have a long enough duration for life to evolve. This means having a stable orbit and conditions that allow for a steady climate over millions of years, providing the necessary time for complex life forms to develop. While the specific conditions may vary, a combination of liquid water, a reliable energy source, essential chemical elements, stable environmental conditions, and sufficient time appears to be fundamental for life to emerge elsewhere in the universe. Scientists continue to explore the cosmos, searching for places where these conditions might align, signaling the potential presence of life beyond our home planet. The search for life beyond Earth has become one of the most exciting areas of modern science. Over the years, scientists have identified several key factors that contribute to a planet's potential to support life. First, the presence of liquid water is crucial. Water is a vital ingredient for life as we know it, and it has been found on moons like Europa and Enceladus, as well as on Mars. These discoveries suggest that conditions might be suitable for microbial life. Next, scientists examine the types of atmospheres present on other planets. An atmosphere can protect life from harmful space radiation and temperature extremes. For example, planets in a star's habitable zone, where conditions could allow for stable liquid water, are of particular interest. This zone is often referred to as a Goldilocks zone because it is not too hot and not too cold. In addition to water and atmosphere, the chemical composition of a planet is important. Elements like carbon, hydrogen, nitrogen, oxygen, phosphorus, and sulfur are essential building blocks for life. When astronomers study the atmospheres of exoplanets, they look for these elements, searching for signs of organic molecules that could indicate biological processes. The exciting news is that scientists have discovered thousands of exoplanets, planets outside our solar system, some of which share characteristics similar to those of Earth. These findings raise the possibility of diverse environments that could harbor life, although any such life might differ greatly from what we understand. Moreover, the more we explore our own solar system, the more we learn about the potential for life beyond Earth.
What if everything we know about the universe is just the beginning of a much larger story? As humanity gazes deeper into the cosmos, we are confronted with mysteries that challenge our understanding and ignite our imagination. This exploration delves into the inheritance of the universe, guiding us through its expansive history into galactic phenomena and those tantalizing cosmic signals that hint at life beyond our world. As we peer into the cosmos, those daring enough to venture toward the farthest reaches of the universe encounter a tapestry of wonders. The edge of the universe, often considered to be the limit of our observational capabilities, presents us with fascinating phenomena, gateways to understanding the origin and evolution of the cosmos. One of the most remarkable features observable in this distant realm is the cosmic microwave background radiation, which serves as a relic from a hot, dense, early universe. This faint glow uniformly permeating all of space is a remnant of the Big Bang, illuminating the story of our universe's infancy approximately 13.8 billion years ago. Another captivating sight at the universe's edge includes distant galaxies. These galaxies are often seen in various stages of development, showcasing the evolution of stellar systems over billions of years. When we look at these ancient galaxies through the lens of powerful telescopes, we do not just see light, we glimpse history itself, revealing the formation and merging of stars and stellar clusters that shape the universe as we know it. Some of the most distant galaxies we observe today are themselves only a few 100 million years old, a mere blink of an eye in cosmic time. Interestingly, we also encounter phenomena such as gamma-ray bursts at the universe's edge. These bursts are some of the most energetic explosions known, potentially signaling the death throes of massive stars or the collision of neutron stars, and they offer us tantalizing insights into the extreme physics governing the universe. Observing these bursts allows astronomers to delve into the processes that govern stellar evolution, as well as the formation of elements that are essential for life. In our quest to understand the universe, we are continually pushed to rethink the boundaries of what lies beyond the observable limits. The further we look into space, the more questions arise, giving rise to new discoveries. Each observation not only fills in our understanding of the universe's history, but also beckons us to explore deeper mysteries waiting in the cosmic expanse that lies beyond. The edge of the universe is not merely a limit, it is a doorway to understanding our place within the grand tapestry of existence. Defining the boundary of the universe is one of the most fascinating challenges in cosmology. Scientists often start this quest by considering the observable universe. This term refers to all the celestial objects and light we can detect and study, stretching out about 93 billion light-years from our planet. The edge of this observable universe is not a physical boundary but rather a limit on what we can see. Any light from beyond this distance has not had enough time to reach us since the beginning of time, known as the Big Bang. Interestingly, what lies beyond this observable horizon remains shrouded in mystery. The universe may very well extend infinitely beyond what we can observe. Some theories propose that it continues indefinitely with galaxies and cosmic structures that we simply cannot see. Furthermore, other hypotheses suggest that the universe could have a curved structure, perhaps allowing for a finite volume, yet without a traditional boundary similar to the surface of a sphere, where traveling in one direction could lead you back to your starting point. Another layer to this definition involves the cosmic inflation theory, which posits that the universe underwent rapid expansion after the Big Bang. This period of inflation set the stage for the cosmos we recognize today and helped shape what we see at different points in the observable universe. It also leads to the intriguing possibility that there could be different regions of the universe, each potentially having its own set of physical laws. While we can define the boundary of the observable universe based on what we can see, the true extent of the universe remains elusive and deeply fascinating. Scientists are continuously learning more using advanced technologies and powerful telescopes to push the limits of our observational reach. This quest not only expands our understanding of the cosmos, but also evokes a sense of wonder about the vastness that remains just beyond our horizon. The vastness beyond our observable universe raises intriguing questions and inspires various theories among scientists and philosophers alike. One widely discussed concept is the idea of an infinity of universes, known as the multiverse theory. This theory posits that our universe is just one among potentially countless others, each with its own unique set of physical laws and constants. Some of these universes might be completely different from ours, while others could resemble ours in intriguing ways. The notion of the multiverse stems from interpretations of quantum mechanics and inflation theory, suggesting that different regions of space could have different properties, resulting in multiple diverse universes. Another fascinating idea is the concept of cosmic inflation, which suggests that the universe underwent rapid expansion shortly after the Big Bang. According to this theory, as inflation pushed regions of space apart, Those regions could create pocket universes, each separate from one another. This means that beyond our observable cosmos, there could exist entirely different realms with distinct characteristics. The fabric of space might be woven with countless threads, each representing a different universe, adding layers to our understanding of reality. Some theories also delve into higher dimensions. String theory, for example, suggests there may be additional spatial dimensions beyond the three we experience daily. In this view, our universe might be confined to a three-dimensional surface within a higher dimensional space. If true, this opens up mind-boggling possibilities about what could exist just beyond our perception and understanding. These extra dimensions could harbor entirely new physical phenomena, leading to realms where the rules differ significantly from those of our universe. Finally, there are speculative ideas about the nature of existence and the possibility of realms shaped by concepts such as dark matter and dark energy. As we probe deeper into the cosmos, we encounter realms we cannot see directly, yet we infer their existence through their influence on the matter we do observe. The nature of these unseen forces may indicate pathways to areas of reality that are beyond our ability to observe at this time, hinting that the universe may be far richer and more complex than our current understandings allow. Each of these theories invites us to ponder the mystery that lies beyond the boundaries of our known universe, keeping our curiosity alive as we explore the cosmos. Black holes are among the most fascinating and enigmatic features of our universe, and they play significant roles even at the very edges at the extremities of the cosmos, where galaxies thin out and the fabric of space begins to stretch. Black holes contribute to our understanding of cosmic evolution and the behavior of matter under extreme conditions. These regions might seem depopulated, but black holes can often be found lurking, hidden from direct observation, yet influencing their surroundings dramatically. There are two types of black holes relevant to our discussion: stellar black holes formed from the collapse of massive stars, and supermassive black holes which dwell at the centers of galaxies. As a galaxy forms, these supermassive black holes can help shape the structure of galaxies by influencing star formation and regulating the chaotic dance of galaxies around. At the edges of the universe, they can affect the movement and fate of surrounding celestial bodies, stemming from their immense gravitational pull. The influence of black holes extends beyond their immediate vicinity. As they consume surrounding gas and dust, they emit powerful jets of energy and radiation, which can illuminate large areas of space. This process not only creates spectacular cosmic phenomena, but also provides astronomers with valuable clues about the early universe and the formation of large-scale structures. These processes at the edge of the universe can help explain how galaxies evolve over billions of years. Moreover, the study of black holes at the universe's edge encourages scientific inquiry into fundamental questions about the nature of gravity, space, and time. As we observe the behaviors and interactions of black holes with their environment, we gain insights into the mysterious forces that govern the cosmos. Each new revelation about these invisible giants extends our comprehension of the universe and highlights how interconnected various cosmic entities truly are, even in the farthest reaches of space. The cosmic microwave background, often referred to as the CMB, is a faint glow of radiation that fills the universe and serves as a critical artifact from the early moments of cosmic history. It is the remnant heat left over from the Big Bang, a moment in time that marks the birth of our universe around 30. By studying the CMB, scientists have pieced together invaluable information about the conditions that existed when the universe was just about 4. When the universe was hot and dense, light could not travel freely. Instead, it bounced around constantly, trapped by the dense plasma of particles. As the universe expanded and cooled, it reached a point where atoms formed, allowing light to finally escape. This transition from a hot, opaque soup to a cooler, transparent state is what we now observe as the CMB. The radiation permeates all of space and is remarkably uniform, with tiny fluctuations that hold clues about the universe's early structure and the seeds of galaxies. These fluctuations in the cosmic microwave background were caused by slight variations in the density of matter in the early universe. By analyzing these minute differences, scientists can infer where galaxies and large-scale structures would later evolve. The study of the CMB has provided evidence supporting the Big Bang theory and has helped refine our understanding of fundamental parameters like the universe's age, composition, and rate of expansion. Furthermore, the CMB has revealed that our universe is not only expanding, but that this expansion is accelerating, a discovery that led to the concept of dark energy. Thus, the cosmic microwave background is not merely a relic of the past. It is a vital tool in unraveling the mysteries about how our universe began, how it has evolved, and the forces that will shape its distant future. Through the lens of the CMB, we can glimpse the underlying fabric of the cosmos and gain perspective on our place within it. As we gaze into the cosmos, we encounter countless mysteries that challenge our understanding of the universe. One of the foremost enigmas is dark matter. This invisible substance is thought to make up about 27% of the universe's total mass and energy, yet it does not emit, absorb, or reflect light. Its presence is inferred from the gravitational effects it has on visible matter, galaxies, and the cosmic microwave background. Scientists are puzzled by its true nature, with many theories suggesting it could be composed of exotic particles that have yet to be detected. Equally enigmatic is dark energy, which accounts for approximately 73% of the universe. This force seems to drive the accelerated expansion of the universe. While we know it exists because of its effects on cosmic scales, its properties remain elusive. The universe's fate hangs in the balance between the effects of dark energy and gravity, prompting fundamental questions about the ultimate destiny of everything we see around us. Are we looking at a future where galaxies drift apart forever, or does some other force await discovery? Another captivating mystery lies in the formation of black holes, especially the supermassive ones found at the centers of galaxies. Their origins are still not entirely understood. How did they grow to sizes millions or even billions of times that of our Sun? Some theories suggest that they might have formed from the collapse of massive stars in the early universe, but this does not completely account for their existence in older galaxies. This aspect of black hole evolution keeps astronomers in pursuit of greater clarity. Lastly, let's contemplate the nature of the universe itself. Many scientists are studying how the universe began and whether it has an edge or is endless in its vastness. The leading theory, the Big Bang, explains the universe's expansion from an initial singular state, yet questions remain about what preceded it and whether our universe is part of a larger multiverse teeming with other dimensions. Each question beckons deeper inquiry, reflecting the boundless curiosity that drives our understanding of the cosmos. It is this quest for knowledge that unravels the mysteries step by step. In the vast tapestry of the universe, dark matter and dark energy stand as two of the greatest enigmas of modern cosmology. Together they account for a staggering 95% of the total energy content of the universe, yet their true nature remains elusive. Dark matter, which does not emit, absorb, or reflect light, plays a crucial role in the structure and formation of galaxies. Without it, galaxies would not hold together. They would simply fly apart due to the gravitational forces of their own star. This invisible mass provides the gravitational glue that binds galaxies and clusters of galaxies, influencing their formation and evolution. While dark matter is linked to the physical structures we can observe, dark energy operates on a much larger scale. It is thought to be responsible for the accelerated expansion of the universe. Since the late 20th century, astronomers have observed that distant galaxies are moving away from us at an increasing speed, a phenomenon that suggests an unseen force pushing them apart. This force, which we call dark energy, composes about 70% of the universe. Its exact mechanics and properties remain a mystery, leading to various theories about its origin and nature. The contributions of dark matter and dark energy speak to the profound complexity of the universe, raising questions about what truly constitutes reality. Copious research is underway utilizing cutting-edge technology and innovative methods. Astronomers hope that by examining cosmic background radiation, the movement of distant galaxies, and the effects of gravitational lensing, they can unravel clues that could shed light on these cosmic puzzles. As our understanding deepens, dark matter and dark energy continue to inspire wonder and curiosity. They challenge our perceptions, compelling us to reflect on our place in an ever-expanding universe. The more we learn, the more we realize there's so much more out there waiting to be discovered, keeping us ever fascinated by the cosmos's mysteries. As we look deep into the universe, we are not just observing stars and galaxies, we are tracing the story of cosmic evolution. One of the most intriguing chapters in that story involves the formation of galaxies at the universe's edge, places that are billions of light years away from us. Here we grapple with some profound unanswered questions that could reshape our understanding of the cosmos. Scientists wonder how these distant galaxies formed so early in the universe's history. When we observe them, we're peering back in time, often more than 13 billion years ago. This raises a puzzling issue. The universe was much smaller and denser back then. So what conditions allowed galaxies to coalesce from gas and dust in such extreme environment? Did they form from smaller clumps of matter that merged over time? Or was there another mechanism at play, perhaps involving dark matter that facilitated rapid formation? Another significant question pertains to the characteristics of these early galaxies. Are they similar to the galaxies we see today? Or do they possess unique features? Observations suggest that they often exhibit significant differences. For instance, some seem to have high rates of star formation that far exceed those in our local universe. Understanding why these distant galaxies are so active could unlock clues about the fundamental processes driving galaxy formation and evolution. Lastly, we grapple with the imprints of cosmic events that these galaxies might reveal. For example, how did the intense radiation from bright stars and supermassive black holes impact the surrounding environments? Such factors could provide insights into how galaxies interacted with their surroundings and shaped the broader fabric of the universe. The answers to these questions are essential, not just for understanding galaxies at the edge of the universe, but for piecing together the entire tapestry of cosmic history. Scientists have an insatiable curiosity about the universe, and understanding its unknown properties is a challenging but fascinating endeavor. They employ a variety of methods, blending observational techniques with theoretical framework. One significant approach is the use of advanced telescopes and observatories, which capture light and other forms of radiation from celestial objects. By analyzing this data, astronomers can infer the characteristics of stars, galaxies, and even distant phenomena like black holes and dark matter. In addition to observations, scientists also rely on experiments conducted here on Earth. Particle accelerators, like the Large Hadron Collider, allow researchers to recreate conditions similar to those right after the Big Bang. These experiments can reveal fundamental particles and forces, refining our understanding of the building blocks of the universe. The discoveries made in these underground laboratories often have implications that stretch far beyond our planet. Computer simulations play an essential role in this quest for knowledge as well. These complex models help scientists test their theories about cosmic events and mysteries, such as the formation of galaxies and the nature of dark energy. By simulating different scenarios, researchers can predict outcomes and compare them with observed data to see if current understanding holds true or needs adjustment. Finally, collaboration is a crucial ingredient in the scientific process. Researchers from various disciplines come together sharing insights that inform their work, whether it's astrophysics, cosmology, or particle physics. These partnerships help piece together the intricate puzzle that is our universe, continuously pushing the boundaries of what we know and widening the scope of discovery. As technology advances and our tools become more sophisticated, the realm of the unknown shrinks, revealing new questions that spark the ever-revolving journey of exploration. Rogue planets, those celestial bodies wandering through space without a parent star, challenge our traditional views of planetary formation and dynamics within the universe. Traditionally, we have thought of planets primarily as satellites of stars, bound by gravitational pulls in stable orbits. The existence of these free-floating planets suggests a more chaotic and dynamic environment in the cosmos, indicating that planetary systems can be far more diverse than previously imagined. The processes that lead to the creation of rogue planets are still being researched, but many scientists believe they may originate from young systems that experience gravitational disruptions, causing some planets to be ejected into interstellar space. This understanding invites us to reconsider how often such events might occur, thereby opening new avenues for investigating the history and evolution of planetary systems. Perhaps many more planets exist in the universe than we have detected, concealed from us as they drift through the void. Moreover, rogue planets may provide unique conditions for the potential emergence of life. While they do not receive light from a star, some theories suggest that these planets could possess internal heat resulting from radioactive decay or the energy left over from their formation. This raises fascinating questions about what forms life might take in such alien environments, and whether life's building blocks can arise in isolation from a sun. Finally, the study of rogue planets emphasizes our place in the cosmos. As they wander alone, far from the warmth of their stellar companions, these planets remind us of the vastness of space and the myriad possibilities existing beyond our own planetary neighborhood. Each rogue planet represents a mystery yet to be unraveled, urging astronomers and cosmologists to continuously explore and reassess our understanding of the universe's complexities. The notion of dimensions beyond our familiar universe is a captivating area in modern theoretical physics. One of the most prominent ideas comes from string theory, which posits that the fundamental building blocks of the universe are not just particles, but tiny vibrating strings. These strings require additional dimensions beyond the three that we perceive to accommodate their oscillation. In string theory, there could be up to 10 or even 11 dimensions, with the extra dimensions being compact and difficult to detect with current technology. Another intriguing concept arises from the multiverse theory. This theory suggests that our universe may be just one of many, each potentially possessing different laws of physics or dimensional structures. Some versions of the multiverse theory propose that these universes exist within a higher dimensional space. In this view, interactions between different universes could create effects we observe in our own universe, hinting at complexities greater than those we can measure. Further expanding on this idea, physicist Kip Thorne and others have explored the potential implications of warped dimensions, where shortcuts through space-time might connect different parts of the universe, or even different universes entirely. These theories have sparked imaginative speculation about the consequences of such dimensions for travel, communication, and perhaps the fundamental nature of reality itself. As research continues, scientists are exploring ways to detect or even visualize these extra dimensions, which remain theoretical for now. The existence of additional dimensions challenges our understanding of space, time, and existence, and hints at a universe far richer and more complex than we can currently perceive. For many, this idea is not just theoretical, it's a doorway to exhilarating possibility, inviting us to consider the limits of our understanding and the very fabric of reality itself. The concept of parallel universes offers a fascinating perspective on our understanding of existence, particularly when we consider the very edge of our own universe. Imagine standing at the boundary of what we perceive as reality. Instead of a hard limit or an empty void, the idea of parallel universes suggests that there are layers of existence waiting just beyond our own. This can completely transform how we perceive not only our universe, but also what lies beyond. When we think of the universe's edge as merely the limit of what we can observe, we recognize a profound sense of isolation. Yet if parallel universes exist, we are compelled to consider that there might be countless alternatives existing simultaneous. Each of these universes could harbor different laws of physics, diverse forms of matter, or even entirely different dimensions of time. This adds a remarkable complexity to our understanding of existence, prompting questions about our reality's uniqueness and the fate of our choices. Moreover, the implications of parallel universes extend to our own identity and consciousness. If there are infinite variations of ourselves thriving in these other realities, it raises intriguing philosophical questions about individuality and existence. We begin to wonder if the experiences we interpret as singular are merely one thread in a much more extensive tapestry of cosmic narratives. This perspective invites a sense of wonder and humility, considering that our understanding is limited to just one version of reality. Ultimately, the idea of parallel universes can offer profound insights into our place in the cosmos. It invites us to ponder our existence, not only as isolated beings in a vast universe, but as interconnected threads in a more expansive multiverse. This can enrich our appreciation of the universe's mysteries and remind us of the endless possibilities that lie beyond our current comprehension. So, as we peer into the unknown at the universe's edge, we may find ourselves not simply at a boundary, but at the doorway to infinite potentiality. The multiverse theory suggests that our universe is just one of many, possibly an infinite number of universes existing simultaneously. Proponents of this theory argue that it offers a compelling explanation for some of the puzzling features of our own universe. For instance, the fine-tuning of certain physical constants, which allows for the existence of life, raises questions about why they have the precise values they do. The multiverse concept posits that among a vast collection of universes, it is not surprising that at least one like ours has the right conditions for life to emerge. On the other hand, many scientists question the multiverse theory, citing its lack of testability. Traditional scientific methods rely on experimentation and observation to validate theories. In the case of the multiverse, it becomes challenging to find evidence that can conclusively prove or disprove the existence of other universes. Critics argue that without empirical evidence, the multiverse remains more of a philosophical idea than a scientific hypothesis. This uncertainty leaves room for skepticism among those who prefer theories grounded in observable phenomena. Furthermore, some opponents of the multiverse theory raise philosophical concerns about the nature of reality itself. If every possible variation of events exists in some universe, it might lead to a kind of nihilism, suggesting that nothing in our universe is uniquely significant. This line of thought invites a discussion on the implications of reality if everything can exist somewhere else. Such perspectives encourage a deeper exploration of what it means to observe and experience our own universe. Ultimately, the debate surrounding the multiverse theory highlights the intersection of science, philosophy, and our understanding of existence. It opens doors to fascinating questions about the cosmos and pushes the boundaries of what we consider possible. As our technologies and methodologies evolve, the quest for evidence continues, and perhaps in the future, we will gain insights that could illuminate or even challenge the multiverse theory further.
As we contemplate the concept of the edge of the universe, we find ourselves at the intersection of profound mysteries and groundbreaking discoveries. The universe, as far as we can observe, is expanding. This expansion suggests that there may be a boundary or edge, although understanding what lies beyond this edge is inherently perplexing. Such a boundary could hold clues about the fundamental laws of physics, revealing insights that challenge our current understanding of space, time, and matter. The edge of the universe might inform us about the origins of cosmic structures. If we could observe this edge, we could gather information about the distribution of galaxies and the cosmic microwave background radiation remnants from the Big Bang. These observations could help confirm theories about how the universe evolved and whether it adheres to the rules set forth by general relativity or quantum mechanics. It may even reveal whether the universe is finite or infinite, a concept that has profound implications for our understanding of reality. Furthermore, probing the edge could provide insights into the nature of dark matter and dark energy. These two enigmatic components constitute most of the universe's mass energy content, but remain largely unobserved. If we consider how the universe behaves at its boundary, we might reveal the underlying physics governing these substances and how they influence cosmic evolution. There exists a possibility that new forces, still unknown to us, could emerge from our explorations of this cosmic frontier. The edge of the universe serves as a tantalizing puzzle, inviting us to rethink and refine our understanding of the fundamental laws of physics. As we aim our telescopes toward the heavens and delve deeper into cosmic exploration, we continue to push the boundaries of knowledge. And who knows what revelations await us at the very edge of it all. The pursuit of understanding what lies beyond captivates not just our minds, but our imagination, urging us ever forward in the quest for cosmic truths. String theory is a fascinating realm of theoretical physics that presents a new way to understand the fundamental building blocks of the universe. Traditionally, particles like electrons and quarks are viewed as point-like entities. However, string theory proposes that these particles are actually one-dimensional strings that vibrate at different frequencies. This small but significant shift changes our understanding of matter and energy profoundly. One of the most intriguing aspects of string theory is how it opens the door to the idea of multiple dimensions beyond the three we experience daily. While we live in a world of length, width, and height, string theory suggests that there could be up to 11 dimensions when accounting for additional spatial dimensions that are compactified or curled up to the point where they are imperceptible. This concept allows for a broader perspective on what exists beyond our observable universe. These extra dimensions could potentially host entirely different structures and reality. Some theories suggest that these hidden dimensions may affect how galaxies form or how gravity behaves at cosmic scale. This could mean that what we perceive as our universe might just be one small slice of a much vaster multidimensional landscape where different strings and their vibrations give rise to the myriad of particles and forces we observe. Moreover, this framework gives rise to the possibility of multiple universes, often referred to as the multiverse. Each universe could have different physical laws and properties shaped by the vibrations of strings within its specific dimensional configuration. While string theory remains highly theoretical and still seeks empirical validation, its implications encourage us to think expansively about the nature of reality and the structures that could lie beyond our traditional understanding of the cosmos. This contemplation of higher dimensions and multiple universes certainly inspires curiosity about the vastness and complexity of what lies beyond our own universe. As we venture toward the elusive edge of the universe, several groundbreaking technological advancements play a crucial role in expanding our exploration capabilities. One of the most significant has been the development of advanced telescopes. These instruments, like the James Webb Space Telescope, are equipped with powerful mirrors and sensitive detectors that allow us to capture light from distant galaxies and stars that formed billions of years ago. This capability not only enhances our understanding of cosmic history, but also helps identify the chemical composition of distant celestial objects. In addition to optical technology, improvements in radio astronomy have opened new frontiers. Powerful radio telescopes can detect radio waves emitted by celestial phenomena, revealing details about star formation, black holes, and cosmic background radiation. These radio waves provide a different perspective on the universe, allowing scientists to study regions that might be too faint or obscured for optical telescopes. Projects like the Square Kilometre Array promise to revolutionize our ability to map the cosmos in unprecedented detail. Digital technology has also transformed our capacity to analyze vast amounts of data. With the rise of artificial intelligence and machine learning, scientists can process information from telescopes more efficiently than ever before. This allows for the swift identification of celestial objects and phenomena, and helps in predicting the behavior of complex cosmic systems. Such advancements make it feasible to translate raw data into valuable insights and progress our understanding of the universe's structure and evolution. Moreover, space exploration missions depend on robust spacecraft technology. Innovations in propulsion systems, such as ion engines, promise to facilitate longer and more efficient journeys across the solar system and beyond.
Further expanding on this idea, physicists Kip Thorne and others have explored the potential implications of warp dimensions, where shortcuts through space-time might connect different parts of the universe or even different universes entirely. These theories have sparked imaginative speculation about the consequences of such dimensions for travel, communication, and perhaps the fundamental nature of reality itself. As research continues, scientists are exploring ways to detect or even visualize these extra dimensions, which remain theoretical for now. The existence of additional dimensions challenges our understanding of space, time, and existence, and hints at a universe far richer and more complex than we can currently perceive. For many, this idea is not just theoretical, it's a doorway to exhilarating possibility, inviting us to consider the limits of our understanding and the very fabric of reality itself. The concept of parallel universes offers a fascinating perspective on our understanding of existence, particularly when we consider the very edge of our own universe. Imagine standing at the boundary of what we perceive as reality. Instead of a hard limit or an empty void, the idea of parallel universes suggests that there are layers of existence waiting just beyond our own. This can completely transform how we perceive not only our universe, but also what lies beyond it. When we think of the universe's edge as merely the limit of what we can observe, we recognize a profound sense of isolation. Yet, if parallel universes exist, we are compelled to consider that there might be countless alternatives existing simultaneously. Each of these universes could harbor different laws of physics, diverse forms of matter, or even entirely different dimensions of time. This adds a remarkable complexity to our understanding of existence, prompting questions about our reality's uniqueness and the fate of our choices. Moreover, the implications of parallel universes extend to our own identity and consciousness. If there are infinite variations of ourselves thriving in these other realities, it raises intriguing philosophical questions about individuality and existence. We begin to wonder if the experiences we interpret as singular are merely one thread in a much more extensive tapestry of cosmic narratives. This perspective invites a sense of wonder and humility, considering that our understanding is limited to just one version of reality. Ultimately, the idea of parallel universes can offer profound insights into our place in the cosmos. It invites us to ponder our existence not only as isolated beings in a vast universe,
but as interconnected threads in a more expansive multiverse. This can enrich our appreciation of the universe's mysteries and remind us of the endless possibilities that lie beyond our current comprehension. So, as we peer into the unknown at the universe's edge, we may find ourselves not simply at a boundary, but at the doorway to infinite potentiality. The multiverse theory suggests that our universe is just one of many, possibly an infinite number of universes existing simultaneously. Proponents of this theory argue that it offers a compelling explanation for some of the puzzling features of our own universe. For instance, the fine-tuning of certain physical constants, which allows for the existence of life, raises questions about why they have the precise values they do. The multiverse concept posits that among a vast collection of universes, it is not surprising that at least one like ours has the right conditions for life to emerge. On the other hand, many scientists question the multiverse theory, citing its lack of testability. Traditional scientific methods rely on experimentation and observation to validate theories. In the case of the multiverse, it becomes challenging to find evidence that can conclusively prove or disprove the existence of other universes. Critics argue that, without empirical evidence, the multiverse remains more of a philosophical idea than a scientific hypothesis. This uncertainty leaves room for skepticism among those who prefer theories grounded in observable phenomena. Furthermore, some opponents of the multiverse theory raise philosophical concerns about the nature of reality itself. If every possible variation of events exists in some universe, it might lead to a kind of nihilism, suggesting that nothing in our universe is uniquely significant. This line of thought invites a discussion on the implications of reality if everything can exist somewhere else. Such perspectives encourage a deeper exploration of what it means to observe and experience our own universe. Ultimately, the debate surrounding the multiverse theory highlights the intersection of science, philosophy, and our understanding of existence. It opens doors to fascinating questions about the cosmos and pushes the boundaries of what we consider possible. As our technologies and methodology evolve, the quest for evidence continues, and perhaps in the future, we will gain insights that could illuminate or even challenge the multiverse theory further. As we contemplate the concept of the edge of the universe, we find ourselves at the intersection of profound mysteries and groundbreaking discoveries. The universe, as far as we can observe, is expanding. This expansion suggests that there may be a boundary or edge, although understanding what lies beyond this edge is inherently perplexing. Such a boundary could hold clues about the fundamental laws of physics, revealing insights that challenge our current understanding of space, time, and matter. The edge of the universe might inform us about the origins of cosmic structures. If we could observe this edge, we could gather information about the distribution of galaxies and the cosmic microwave background radiation, remnants from the Big Bang. These observations could help confirm theories about how the universe evolved and whether it adheres to the rules set forth by general relativity or quantum mechanics. It may even reveal whether the universe is finite or infinite, a concept that has profound implications for our understanding of reality. Furthermore, probing the edge could provide insights into the nature of dark matter and dark energy. These two enigmatic components constitute most of the universe's mass energy content, but remain largely unobserved. If we consider how the universe behaves at its boundary, we might reveal the underlying physics governing these substances and how they influence cosmic evolution. There exists a possibility that new forces, still unknown to us, could emerge from our explorations of this cosmic frontier. The edge of the universe serves as a tantalizing puzzle, inviting us to rethink and refine our understanding of the fundamental laws of physics. As we aim our telescopes toward the heavens and delve deeper into cosmic exploration, we continue to push the boundaries of knowledge and who knows what revelations await us at the very edge of it all. The pursuit of understanding what lies beyond captivates not just our minds, but our imagination, urging us ever forward in the quest for cosmic truths. String theory is a fascinating realm of theoretical physics that presents a new way to understand the fundamental building blocks of the universe. Traditionally, particles like electrons and quarks are viewed as point-like entities. However, string theory proposes that these particles are actually one-dimensional strings that vibrate at different frequencies. This small but significant shift changes our understanding of matter and energy profoundly. One of the most intriguing aspects of string theory is how it opens the door to the idea of multiple dimensions beyond the three we experience daily. While we live in a world of length, width, and height, string theory suggests that there could be up to 11 dimensions when accounting for additional spatial dimensions that are compactified or curled up to the point where they are imperceptible. This concept allows for a broader perspective on what exists beyond our observable universe. These extra dimensions could potentially host entirely different structures and reality. Some theories suggest that these hidden dimensions may affect how galaxies form or how gravity behaves at cosmic scales. This could mean that what we perceive as our universe might just be one small slice of a much vaster multi-dimensional landscape, where different strings and their vibrations give rise to the myriad of particles and forces we observe. Moreover, this framework gives rise to the possibility of multiple universes, often referred to as the multiverse. Each universe could have different physical laws and properties shaped by the vibrations of strings within its specific dimensional configuration. While string theory remains highly theoretical and still seeks empirical validation, its implications encourage us to think expansively about the nature of reality and the structures that could lie beyond our traditional understanding of the cosmos. This contemplation of higher dimensions and multiple universes certainly inspires curiosity about the vastness and complexity of what lies beyond our own universe. As we venture toward the elusive edge of the universe, several groundbreaking technological advancements play a crucial role in expanding our exploration capabilities. One of the most significant has been the development of advanced telescopes. These instruments, like the James Webb Space Telescope, are equipped with powerful mirrors and sensitive detectors that allow us to capture light from distant galaxies and stars that formed billions of years. This capability not only enhances our understanding of cosmic history, but also helps identify the chemical composition of distant celestial objects. In addition to optical technology, improvements in radio astronomy have opened new frontiers. Powerful radio telescopes can detect radio waves emitted by celestial phenomena, revealing details about star formation, black holes, and cosmic background radiation. These radio waves provide a different perspective on the universe, allowing scientists to study regions that might be too faint or obscured for optical telescopes. Projects like the Square Kilometre Array promise to revolutionize our ability to map the cosmos in unprecedented. Digital technology has also transformed our capacity to analyze vast amounts of data. With the rise of artificial intelligence and machine learning, scientists can process information from telescopes more efficiently than ever before. This allows for the swift identification of celestial objects and phenomena, and helps in predicting the behavior of complex cosmic systems.